Hello. Today we're going to talk about Faraday's law, and this is an introduction to Faraday's law. Hopefully, you've seen a demonstration either in person or on a video about Faraday's law. And Faraday's law is pretty simple, but before we do that, if you need a moment to sketch the picture on the right there, go ahead and take a moment and pause the video. All right. Um, we're going to talk about Faraday's law in general. And if you saw the demonstration, basically it's very simple. If you change the magnetic flux through an area, then you get a voltage, an EMF. Okay. So EMF is short for electromotive force, which is basically the old-fashioned term for voltage. Um, and the symbol for that is a fancy-looking E. Now, before we do that, though, let's talk about the magnetic flux. So you might recall, hopefully, from previous unit, that magnetic flux is equal to the double integral, because it's an area, of B dot dA. Okay. Now, looking at that picture on the right there, assuming B is constant throughout that region, then you can just write this as B times A. Oh, and I'll get rid of the vector now. We're looking at just magnitudes. So B times A, and then times, if it's a dot product, that involves cosine of the angle that's there. Okay. Now, technically, the flux entering the area on the top would be a negative, and the flux leaving the bottom of that circle would be a positive. But right now, we're just worried about the magnitude of the flux. So it'd be BA cosine theta. Now, what Faraday's law says, and this is one version of Faraday's law, is EMF. Okay, and it's a fancy looking E, but really all this is voltage. And we just use this symbol as a way to denote voltage created in this way versus, like, let's say voltage created by a battery, which is a little different. Okay, same unit, same thing, but it's just created differently. Okay, so any voltage created this way, we use that fancy looking E. And Faraday's law is pretty simple. It's negative d magnetic flux dt. So the rate of change of magnetic flux. Now, that negative sign, we're going to talk about that later. That has to do with the direction that the electric field and therefore the current flows in that loop. That's something called Lenz's law. That's coming up pretty shortly here. But for now, what you're worried about is the magnitude, d flux dt. And one modification that you'll often see to this is sometimes they'll put an N in front of it. So, for instance, if you had a second loop here, okay, then you'd have a 2. So you'd put a 2 in for N. So N is simply the number of loops you might have, okay? Now, for the magnetic flux, there are many, many ways to change this, okay? If I kind of put this in for flux, then your EMF, and I'll leave the negative there, but again, it's just a direction thing. You can take the negative n times the time derivative of BA cosine theta. Okay, so here's the idea. If you change the magnetic field, or you change the area of that loop, or you change the angle of that loop, you change any of those three things, then you're going to get a voltage around that loop. You're going to generate an electric current in that loop as well. Okay, and by the way, this is basically how all of our electrical power is generated. This is how in Illinois we have Commonwealth Edison. This is how they generate the vast majority of their electric power. So like whether it's a coal-fired power plant or windmill or wind turbine or hydroelectric or nuclear, they all work the same way. It's all roughly this, okay? And we're going to get into a lot of those details as we go. So that's the intro. Now here's what I'm going to do. I'm going to do 2 quick examples with you, and then I'll do 2 more in a separate video, okay? So we'll call this first one example 1, okay? And let's say I give you a problem where area is going to shrink. So let's say it's some starting value and then divided by t squared. So as time goes on, the area is going to get smaller and smaller, like you're crushing the loop. Let's say b is constant. Let's just say it's a b naught. Let's say the angle is 0 degrees between the area vector and the magnetic field. So this thing, the loop would be horizontal, the area vector would be pointing vertically upward. Okay. What would the EMF be in this particular case? So EMF would be negative d magnetic flux dt, which is negative derivative of BA cosine theta. Well, theta is 0, so cosine of theta is 1, and that's a constant. And I'm telling you B is constant. So really, all you're going to have here is B dA dt. And I'm going to drop the negative because I'm only worried about the magnitude of it. Okay. So the magnitude of the EMF would be B times the derivative of A, which is negative 2 t to the negative 3 and then times A naught. Okay, so you're taking the derivative of t to the negative second, so it'd be negative 2 t to the negative 3 A naught. And that's just your answer. You can tidy it up a little bit. Again, the magnitude of this would be 2 B naught, okay, A naught over T cubed. So that would be your magnetic, or that'd be your EMF, that voltage for that loop. Notice the voltage just changed with time. Second example, again, another quick one. Let's say I've got an example where the magnetic field changes. So let's say B equals B naught times 1 minus e to the negative kt. Okay. Now notice that field starts off being 0 because you got e to the 0, that's 1, then 1 minus 1 is 0. And then the magnetic field becomes B naught after a short time. After when time gets really big, e to the negative big number is 0, so you get B naught times 1. This would be like the demo you saw where somebody's adding a magnet to a coil of wire. In the coil of wire, there was no field, and then a short time later, there is a field that stays there. So this would be a model of you placing a magnet into a coil of wire. Okay. Let's assume that the area doesn't change, and let's assume the angle between the area vector and the magnetic field is 0 degrees, so we don't have to worry about that. Okay, so you're just basically placing a magnet in a coil of wire. Well, for now, will be a single loop. We'll do a single loop of wire. So your EMF is, the magnitude of it is d magnetic flux dt, okay, which is the time derivative of BA cosine theta. And again, the A isn't changing and the cosine theta is just 1. And so you end up with area times dB dt, okay? So that's what's varying with time is the magnetic field. And so if we take our derivative, the EMF would be area times B naught times the derivative of 1 is 0 minus the derivative of e to negative kt is negative k e to negative kt. Our negatives drop out, and we wouldn't really care anyway because we're looking for the magnitude. And you get a b naught k e to the negative kt. Okay, so that would be your EMF as a function of time. Notice that after some time goes by, e to the negative kt becomes 0, and your voltage is 0. So when you notice in the demo, when they put the magnet in the loop, there was a voltage for a short time, and then the voltage dropped to 0 when the magnet stopped moving and when there was no more change in magnetic field or magnetic flux. If you had more than one turn of wire, so for instance, you had a solenoid, and this was in the demo, the more turns you would have, you just multiply this whole thing by n, the number of turns that you might have. And that would be the only change. All right, I got 2 more examples for you in the next video.